We need to remember that when the Ethernet frames, that is the 802.3 or Ethernet 2 frames are transmitted over the network, at the end of the frame, we have typically the frame check sequence. The frame check sequence are bits that are used in order to detect if an error occurred during the transmission of the frame over the network. In the case of Ethernet, we use an algorithm called cyclic redundancy check, and that is what is performed, and we will study now. Typically, for instance, if this is the content of the frame that need to be transmitted over the network, we use a particular channel encoder that generate bits called the test bits, or in the case of Ethernet, the frame check sequence bits. This channel encoder use an algorithm called CRC, cyclic redundancy check, and then the data, the original data of the message plus the test or control bits are transmitted together over the network. In this picture, we could see that this is the sender, this is the receiver, in order to transmit the original data. For instance, the typical frame with the payload and even the header of the frame. We calculate some bits that we transmit appended at the end of the frame to the useful data of the frame. And in order to calculate these test or control bits, called typically CRC bits or cyclic redundancy bits, we need to divide all these sequence of bits of all these bits chain or bit stream, where we complete the data with n bits in 0 at the end. Then we perform a division of this number by this divisor. This divisor it has a length of n+1 bits, and the remainder of the division is a number of n bits. That is the CRC, and these n bits are then appended to the data to be transmitted over the network. If we need to understand that over the network, there could be happening some impairments. For instance, typically burst noise, impulsive noise, and that kind of phenomena modify the bits that are transmitted over the network. And in the event of the happening of that kind of errors, that are random errors or burst errors, the CRC it's a good mechanism to detect the occurrence, the happening of that kind of errors. In the side of the receiver receives the data bits and the CRC bits, and calculate the same calculation that was performed before by the sender, but in this case, this division, the division of this data plus those CRC bits divided by the same divisor would have a remainder of 0, all the n bits in 0. If this remainder is different from 0, means that the frame received have had experienced errors during the traveling across the network. In order to then better understand the CRC mechanism, we need to pay attention at some concepts. First, the detection of transmission error is performed using redundancy. That is, this information, those n bits are redundant information, because this information is deduced from this original information. Then this is not a new information, but the derived information from this one, and that's why we talk about redundant information. The other concept that we need to be aware is that the CRC procedure is only designed for the detection of random or burst errors, but is not suitable to ensure the integrity, for instance, the case of man-in-the-middle attack. If somebody, I mean, if there is a malicious intention of some entity, could be a person or could be a process, an algorithm that modify maliciously the information that is traveling, the CRC is not the suitable mechanism to detect that kind of scenario of errors. The cyclic redundancy check is based on the representation of bit change as a polynomial with coefficients of 0 and 1. And the modular 2, because each digit has only two possible states, 0 and 1, then modular 2 is used for the calculation with polynomials. There is no carryover in addition and no borrowing in subtraction. The cyclic redundancy check is a so-called linear code with m linearly independent generator words, that is G1, G2, G3, Gm, that is m digits, which are derived from a generator pattern by position shifting. And this generator pattern, as well as the code word, can be written as polynomials in where u is typically a variable, depending on the algorithm used for the CRC calculation. This example, for instance, we could calculate cyclic redundancy of linear code constituted by m is equal to 4, for instance, 4 data bits. K is equal to 3 because 4 plus 3 is equal to 7. That then this is the length of the message, of the whole message, and this is the length of the original data, and this is the length of the test or control bits. And for polynomial arithmetic, modulo 2 is used. That is, the overflow carry is not considered. And you need to know that in order to perform addition and subtractions, use the operator exclusive OR. Remember that the exclusive OR is an operation where the XOR of 2 zeros is 0, the XOR of 2 ones is 0, the XOR of 1 0 and 1 is 01. That is used in order to perform that kind of operations, that is the division of this bit chain or bit string by this divisor of n plus 1 bits. Then here we could see an example of generator pattern, that is the typical divisor that we need to use to calculate the remainder of the division. For instance, if the generator pattern is this one, then this is the polynomial representation of this pattern. And if we eliminate from this polynomial expression the terms that has coefficients 0, then this is the final expression of this generator pattern. And then, for instance, we could see, for instance, in this case, those are the standard polynomials proposed in different by different standards and technologies. Typically, this is the CRC proposed by the CCITT. That is what we now call the ITU, the International Telecommunication Union. This is a pattern of 17 bits, digital bits, but in fact, with this polynomial generator, we could calculate a CRC of 16 bits. And this one is the polynomial used in Ethernet, that is CRC of 32 bits. Remember that always the generator pattern has the highest and the lowest bit in 1. For instance, in this case, the lowest in 1 and the highest in 1 too. And if we use polynomial generator pattern like this, we could detect the burst errors of length of 16 bits with 100% of efficiency or of efficacy. Then, in this case, for instance, we could perform an example. If this is the data that we need to transfer, we complete and we will use this generator pattern, for instance. In this case, for instance, this generator pattern could be this one, CRC CCITT, but of 4, and That means that we transmit 3 test bits with this generator pattern, and then we need to, in order to calculate the CRC code, we need to divide this data multiplied by 3 bits. That is, we append 3 zeros at the lowest part of this number. We divide this number by this generator pattern, and the remainder of the division is typically this number of 3 bits. And this is the number that we append to the data and transmit this information across the network. The other side of the network, in the receiver side of the network, the receiver performs a verification dividing this information, the bit chain, by the generator pattern. The remainder of this division is used to determine if an error happens during the transmission across the network or not. If the remainder is 0, then no errors occur. But if this remainder is different from 0, means that an error is detected, and in that case, in the case of Ethernet frames, the Ethernet frame must be discarded. Then, in order to understand how this algorithm is implemented, we need to know that it's very easy to implement using linear feedback shift registers. The shift registers are electronic devices that receive the bits and transfer the bits from one digit to the following bit, and in that way we perform the typical division operation. And in order to divide the data by the generator pattern. Remember the generator pattern. For instance, in this case, in this example, we have this one. This one corresponds to the CRC CCIDT, that is this one, where we have a 1 at the 0 position, at the 5th position, at the 12th position, and at the 16th position. Then this is accomplished using this kind of XOR operators. In this XOR, we are taking into account the 16-bit. In this XOR, we are taking into account the 5th, and yes, in this one we are taking into account the this coefficient, this one this coefficient, and in this one this and this, depending on the time in which we insert the bits in the shift register. What is important to understand that if you insert a lot of bits into to this shift register, finally we will get a number of 16 bits that are the CRC using this polynomial generator. Then what is important to understand, to realize, is that we use the CRC algorithm to calculate redundant information. Typically, if this is an Ethernet frame, this is the frame check sequence that is calculated using an algorithm of cyclic redundancy check, and the algorithm used in the Ethernet networks is this pattern that we see here. This one that is a pattern that permits to calculate a CRC of 16 bits. And in that way, we could perform this kind of procedure. In the sender side, we calculate the CRC, and we append the CRC bits to the data. With the CRC and the data in the receiver side, we calculate the CRC, this check, and the division of this bit chain by this divisor pattern generator. We have to get as a reminder 0, but if the remainder is not 0, means that an error is detected, and in that case the frame, the Ethernet frame, must be discarded.